If you want to predict cognitive decline in Alzheimer's disease, you don't count plaques and you don't count tangles. You count synapses. The standard assumption in the field has been that this synaptic loss is a direct precursor to cell death, that stripping a neuron's connections inevitably and proportionally causes its execution. The data contradicts this. In the CA1 region of the hippocampus, stereological counts reveal that roughly 55% of synapses are already gone in mild Alzheimer's disease, before any neuronal cell loss is detected. Even at the end stage of the disease, up to 3/4 of these vulnerable neuronal profiles remain physically viable in the brain, despite massive deafferentation. A cortical neuron can lose half its synapses and survive. The proportional relationship between structural pruning and cellular execution is biologically false. In fact, losing synapses should technically make a neuron safer. Synaptic transmission and the ion pumping required to reset those electrical gradients constitute the dominant energetic expense of gray matter. A cell stripped of half its synapses has shed half its metabolic burden. Furthermore, the brain has a built-in mechanism to correct for a loss of input: homeostatic synaptic scaling. When synapses disappear, the neuron multiplicatively increases the electrical weight of its remaining contacts to hold its average firing rate steady at a specific set point. Between a reduced metabolic cost and a perfectly recovered electrical output, a partially pruned neuron appears stable and compensated. If subtraction relieves physiological burden and homeostasis restores electrical output, we are left with a mechanical vacuum. By what mechanism does a tolerated loss of synapses ever convert into a lethal execution? The disease does not cause blunt passive structural damage. It co-opts highly regulated, active biological programs to remove these synapses. This chart shows two specific causal pathways of elimination. On the left, amyloid beta drives the degradation of FB2. This reactivates a developmental spine-repression pathway that usually only operates to refine circuits in the growing brain. On the right, the complement fragment C4D binds to the neuronal receptor LILVRB2. This acts as a signal instructing the neuron to autonomously dismantle its own spines. We know these mechanisms are causal. In animal models, genetically blocking either of these pathways rescues the synaptic network, completely independent of the total amyloid burden. Because these are physiological editing tools operating exactly as designed, they strip the circuit apart efficiently without triggering a generalized cellular alarm. If the cell doesn't trigger an alarm and synaptic scaling keeps its firing rate stable, the neuron still eventually dies. A neuron purchases its survival through a process called trophic settlement, specifically the BDNF and CREB-driven transcriptional programs that maintain cellular health. This graph illustrates the mechanical flaw in the neuron's compensation. Trophic support is not delivered to the cell in bulk based on total electrical output. It is purchased locally per synapse. When synaptic scaling doubles the electrical weight of surviving contacts to maintain that flat firing rate, it does not double the number of BDNF-secreting sites. This survival loop operates on positive gain. When a spine is lost, the total trophic output falls, which immediately reduces the cell's capacity to maintain its remaining spines. The cell decompensates structurally while appearing perfectly compensated electrically. It is an invisible starvation. As that starvation sets in, the actual machinery of cellular execution is already running. The canonical executioner is caspase-3.
Caspase-3 is active pre-symptomatically, but it is restricted entirely inside individual dendritic spines to execute localized pruning without harming the main branch. The neuron survives this dangerous process through strict compartmentalization. Local calcium buffering and proteostasis form a containment wall that prevents the active caspase from diffusing. Somatic cell death is not the sudden decision to recruit a new executioner. It is the mechanical failure of that local compartmentalization. Age-related stressors and trophic starvation deplete calcium buffers like calbindin. When those containment walls fail, the destructive program spills directly into the soma. The disease does not invent a novel way to kill the cell. It simply removes the walls around a destructive tool the healthy neuron has safely used thousands of times. The consequence of one cell failing cascades immediately through the functional network. When an upstream neuron dies, or merely retracts its axon, the downstream target experiences deafferentation. This animation shows how that physical withdrawal instantly debits the downstream target's trophic account. Because survival is calculated per synapse, losing an incoming connection immediately drops the receiving cell's trophic score by that exact same arithmetic. This places the downstream neuron on the exact same accelerating downward trajectory, forcing it to withdraw its own connections one synaptic generation later. Degeneration spreads along anatomical pathways purely through mathematical subtraction, without requiring network hyperactivity or the physical transfer of toxic proteins. Large-scale brain hubs are vulnerable precisely because connection is the currency of survival. Highly connected nodes have the most synapses to lose, making them mathematically the most exposed. What then determines the exact tipping point where a tolerated subtraction finally breaches containment and becomes a lethal execution? The lethal threshold is set cell-autonomously by specific local lesions. Variables like tau targeting fine to the postsynaptic density or an ApoE4-dependent derangement of the proteasome lower a specific cell's ability to tolerate synapse loss. This chart reveals how individualized breaking points manifest macroscopically. The top line tracks lesion burden, rising exponentially. The bottom line tracks neuron number, falling linearly. If neuronal execution were a simple dose response, the cell death curve would match the exponential pathology curve. A linear cumulative loss beneath a rising tide of pathology proves that cells are not dying from a universal toxic dose. They die sequentially, as an accumulating subtraction sweeps across their individualized breaking points. This model accounts for the long-standing scarcity of identifiable apoptotic cell death in post-mortem Alzheimer's tissue. Over a decade, a single cell is the site of roughly 10,000 localized, sublethal spine elimination events. Morphological somatic death is only visible for a clearance window of roughly 6 to 24 hours. That narrow window renders the final execution statistically invisible to standard sampling. The evidence was always one compartment down. A neuron that has lost most of its connections and fallen silent contributes nothing to a patient's cognition. This structural reality dictates a change in our clinical strategy. Protecting a silent, disconnected cell body might produce a clean histological result, but it offers the patient no functional benefit. The operative lesion of Alzheimer's disease is disconnection, not death. Clinical trials must prioritize anti-elimination targets like the C1q-C3 complement pathways, measured by in vivo synaptic density PET scans, rather than waiting to rescue isolated somata.